because you're co-host.
Okay. I've been using a little bit more Zoom lately, so I think I'm getting the hang of this. I was teaching a summer class at the University of Pittsburgh that was fully online, and we were running the video part through Zoom. So,
well, we've been doing it for 1.5 years, so now we are pros at it.
Well, we're starting back to school tomorrow.
Great.
And, but I'm fully in person now, I'm glad to say.
Congratulations.
The only thing, yeah, thanks. Although we were supposed to start without wearing masks as long as you were vaccinated, but we've had some rise in cases locally. So they're thinking, well, we'll put everybody in masks. My only worry now is that it's going to discourage students if they don't see an immediate benefit from getting vaccinated. But we've got a few other things that we ought to be able to encourage them in for there. Hopefully this won't be too long.
Yeah, let's hope.
That
it's already been long, too long.
Now, I need, all right, I've got one page there. All right, so share screen.
And Tim, we don't have your chapter for today.
No, so unfortunately, this is one which is new to me. I don't have it written up as a book chapter yet because I haven't tried teaching this yet. This is actually something new, although I did have a research student with it. And let me check now. I've got.
Actually, I even had students asking me for where is the book, for which the chapters belong.
They're starting to get used to this. Well, that'll just motivate me to get this thing written up properly.
Yeah, I think it's already written so well. It's almost done. Yeah.
Well, I mean, also adding this in as a chapter then. I found out as I was getting the talk prepared, though, that I had not properly understood some of the equations that I'm using, and I'm winding up using a graphical form of it here in the end, is what I wound up doing. Now, let me make sure here. Is everybody seeing the, it looks like.
You need to go on screen share mode. Go to slideshow mode.
Okay. Now,
now perfect. It's perfect. Yeah.
Okay.
So, yeah, thank you. So I'll be out now.
What I am, and then put on the chat window as well here so I can see any questions that come up. All right. So what I'm going to be teaching you all, I was about to say tonight, this morning, is about how to, doing a little bit of planetary science. This is a real departure from the work that I usually do. I'm an extragalactic astronomer, so I deal with galaxies, quasars, black holes, and that sort of thing. I'm not used to dealing with things in the Milky Way very much. Although I have done some with the planets, the exoplanets, but getting down to the actual rock and dirt of the planet's surface is very new to me. But this is something which I came across in an excellent book, which I'll show you all in a little bit, called Moons and Planets by William K. Hartman. He is a planetary scientist at, I forget where he teaches. He's at one of the colleges in California. And
could you please spell the author on the chat window?
Yes. Let me
type
this in here. Let me put it to everyone. Moons and Planets by William K. Hartman. Now, William K. Hartman is well known among planetary scientists. The interesting thing to me is I had known of him back when I was in high school. And I bought a book of his called Cycles of Fire, which was simply artwork of planets, hypothesized planets around other stars and such. And it was beautifully done artwork. But it turned out when I went to what we call in America a governor's school, this is the state of Tennessee has set up a school, a summer program for top high school students to go to. We would take kind of college level classes, but really just developed for us in different subjects. And we would have these guest speakers coming in each night. And one of them was William K. Hartman. And he was talking about the formation of the moon and other planets and so on. And it just happened that I brought this book along with me. Well, I went up and got to talk to him afterwards and got him to sign the book there, but it was a nice coincidence. But it was only later that I found out that he was widely known as a planetary scientist, and his artwork was simply just off on the side there. He illustrates some of his own books. Anyway, so I found in this book, Moons and Planets, that you can measure the age of the surface of a planet by looking at impact craters. So let me go through the background of why this works at all. All right. Oh, wait, why am I not going forward? There we go. So how did the solar system form? Well, we've got here in the center, we've got our early sun, which you see here, and surrounding it is what we call a protoplanetary disk. You may have seen photographs of this from the ALMA observatory, which has been come online in the last 5 years or so, which is a sub-millimeter wavelength, kind of short wavelength radio observatory in the Atacama Desert in Chile. And ALMA has actually been able to get photographs of precisely this. And these pictures may have been taken before the ALMA photographs came out. I'm not really sure. This artist rendition here, but maybe this is a post-ALMA. They've been able to see these gaps in the disk, which are formed by the giant planets sweeping up gas and dust in their own orbits, and clearing out these bands. I should have included an ALMA picture there. So what happens is that you get a big nebula in space, gas and dust. Dust is important for this. It starts to collapse under its own weight, and it's spinning because everything is spinning. There's no reason for it not to. It has a little bit of angular momentum. And as it collapses, well, as the radius decreases, the angular momentum must stay the same. And so the rotation rate has to increase. But as it spins faster, it flattens out. Now imagine, I don't know if pizza is a popular dish in India as it is here in America, but if you've ever seen, maybe in the movies, seen somebody making a pizza crust, and he takes the dough, balls it up, and then he spins it and tosses it up in the air as he spins it, and it flattens out. Well, you get this rotational flattening. That is a known process. It happens with a lot of kinds of materials. And it flattens out from a big cloud into a disk. And as it does so, then the density increases and you start to form planets. Well, the early stages are really protoplanets, the first stage of planet formation. And these collide with each other and they form larger bodies, solid bodies, which are the finally become planets. There's still some debate over exactly how the gas giant planets are formed, the Jovian planets, whether a large core, rocky core, forms first and collects gas around it, or whether you get a big ball of gas from an overdense region in the cloud, and that attracts protoplanets into it that then form the rocky core. But that doesn't really matter for our purposes here. What matters is that you see that we have all of this extra material left over. We have large planets here, and we have small planets as well. But you've also got all this debris running around. Well, this debris is orbiting the sun just like the planets are, but occasionally it runs into it. Some of the stuff that's left over after all of this are the asteroids that we have today, for example. And we occasionally get asteroids that collide into the existing planets. The comets as well. Most of y'all will not be old enough to remember Comet Shoemaker-Levy 9, which was discovered in 1994 and spectacularly collided with the planet Jupiter and was watched by the Hubble Space Telescope. The first time a comet had been witnessed to impact a planet in history, at least that we know of. And this had confirmed the idea that there are that these collisions are an important process of how the solar system formed and what still goes on today. So let's take an example of that, a very particular one, the formation of our own moon. Now, what is believed is that the Earth had formed 4.5 billion years ago and was sitting around there orbiting the sun and minding its own business, when a Mars-sized planet, which the planetary astronomers call Theia, Theia, Greek name there, collided with the young Earth and remelted, the heat from the collision remelted the surface of the Earth. There is no hole left over from this collision. And it knocked a lot of material back out into space, which formed the moon. Now, here we have a schematic for this here. Here's our Theia in red, a nice Mars color, hits the early Earth 4.2 minutes after impact. It's a very precise number, but this is coming from computer simulations of it. It has distorted it that much, and it rips open a big section of the Earth here 8 minutes later. This is a very fast process. And then after just 2 hours, then you see that it's pulled out this big glob here. Some of that drifts off into space, but a lot more of it goes into a ring around the Earth. And over time, maybe millions of years, that consolidates into our moon. Notice also that the tilt in the Earth's axis, the obliquity of the ecliptic, as we call it, 23.5 degrees, comes about from that impact. You may notice, by the way, that nearly all of the planets rotate around their own axes in the right hand rule. So if you take your right hand with a thumb as the North Pole, and then the fingers of your right hand curl in the direction the planet rotates around that North Pole. Well, the Earth does this and so on like that. The Earth rotates on its own axis in the same counterclockwise direction, as you look down onto that North Pole, as it orbits around the sun. The moon orbits around the Earth in that same counterclockwise direction. And all the planets orbit the sun in the same counterclockwise direction. Their moons go around counterclockwise, and they rotate counterclockwise, with one exception, and that's Venus, which rotates clockwise, and it very, very slowly. I should also say that Uranus and let's see here, Uranus and Pluto both have their North Poles tilted almost about 90 degrees from what ours is. And so all of these that have such a great angle or backwards rotation, we think come about from these early kinds of collisions, because a lot of material was floating around in space and smacking into the planets then. All right, now, so we got the moon, which formed from one impact. Now let's take a look at what the moon looks like from the Earth. There's a great photograph of the full moon. Now, probably you are familiar with this, but we have these light areas, which are the lunar highlands, and then we have these very dark areas, almost black. These are called the seas, or maria. Mare in singular, maria in plural, is the Latin word for the sea. And so these were looked at by early astronomers as reminiscent of oceans, and maybe were thought to be physically oceans there. And so they got their names this way then. So these maria are basalt. And I may have the geology wrong, but they're basalt, and they're a very dark material, and they're distinctly different from the highlands and the bright colors. Let's take a look at the names of some of these here. Mare Imbrium, Mare Frigoris, that's if you've taken any Latin, that's the frigid sea. The Mare Serenitatis, the sea of serenity. Mare Tranquillitatis, the sea of tranquility, which is where Apollo 11 landed in 1969. You may remember the famous words of Neil Armstrong when they touched down, which was Houston, Tranquility Base here, the Eagle has landed. Well, Tranquility Base, named for the sea of tranquility. And Mare Crisium, the sea of crises. Not all of these are such tranquil names then. Sea of humidity, Mare Humorum, and so on like that. Okay, so these are the seas, the mare, the maria. Now, this is what the moon looked like to everybody from prehistory right up until the space age. No man had ever seen what we call the dark side of the moon, the far side. Now, some people will tell you that calling it the dark side of the moon, I don't know if that's common in India, but it's the common name in America, and then I guess maybe generally in English too. Dark in this case does not mean that it is without light. It means that it is unknown. It's metaphorically dark. Okay, there's no knowledge about it, and there was no knowledge of the dark side of the moon until the Russians. They got the first spacecraft in orbit around the moon, and they brought back pictures of it. And they also wound up naming a lot of the features on the back. So you see Russian names. So all of a sudden, we discovered that the dark side of the moon looks very different from the side facing the Earth. And what you notice is the absence of the Maria. There are no seas. Well, there's one. There's the Moscow Sea. That's that big one there. And I forget the name of this little one over here then. But they are very small. And the reason for this, we understand now, is that the Earth has been protecting the moon from impacts, and the moon has been protecting the Earth. But because only one side of the moon faces the Earth, then the other side is subjected to constant impacts then that create craters, that dig up the soil, and that make the bright colored regolith, that's the lunar soil, that broken up into small pieces there, which makes it the bright colors. Why did the Maria form? Well, the idea that we have is, imagine that you've got a sequence on the, sorry, this is a sequence of pictures. Imagine you have a region on the moon here on the left-hand panel. It's got craters, it's got variation on it. Now, you get a big asteroid smacking into the moon. And about 3 to 3.5 billion years ago is when these happened. And it creates a deep crater, a wide crater like this. But more than just that, it cracks the crust of the moon. And the moon had, especially back then, it had, just like the Earth, a molten core and a magma layer above that. So the magma seeps out through the cracks and it fills in the low-lying areas of that giant impact crater basin. And so you've got then, for a long time, possibly millions of years, you would have then glowing lava coming out through that. And then it would slowly cool, and then it forms a basalt flat region called the Mare. And that is because it's basalt, it's much darker, but also notice that it is nearly free of impact craters, and that's because it's a much younger surface. Now, I'm getting a little bit ahead of the game here. The thing is, we didn't know about all of this until very recently. Has anybody seen this before? Does anyone know where this is? Just type in the chat window if you recognize this location here. I'll give you a hint. It's in the United States. All right, I see. Yes, okay, there are a few of you who know of this. This is popularly called Meteor Crater in Arizona, but that's not the original name. It's called the Behringer Crater, named after the man who discovered it back at the beginning of the 20th century, or in Spanish, Canyon Diablo, Devil's Canyon, which is a great name for it as well. Now, this is, well, we didn't know what it was. When Mr. Behringer discovered it, he had actually hypothesized it could be an impact of an asteroid or something like that. But actually, fairly quickly, a rival theory was come up with, which was that it is a volcano. And maybe more specifically, an eruption of steam from a volcanic vent down below. And so impact craters were simply unknown. After all, it was simply a hypothesis. But volcanoes are very well known, and there are a lot of volcanoes in Arizona, I should note, largely extinct ones. But so the volcanic idea was the popular idea for a long time. There were still, people had thought maybe it could be an impact of some kind, but there was really no way to tell. But there was a young geologist named Eugene Shoemaker, spelled exactly how it sounds, Shoemaker. And he was interested in the idea. Thank you for posting that there. He was interested in the origin of this there. And he got a chance to witness a nuclear bomb test in Nevada. And back then, when we were doing the tests above ground or on the surface, then, of course, they would leave a crater. And actually, it's once the radiation dies down and the fallout goes away, then it's safe to climb down in there with appropriate precautions. And he had found down in that shocked quartz. And was able to find the same kinds of mineral, broken quartz mineral, in the Behringer Crater in Arizona. And he was able to figure out that the pressure needed to create this was too great for anything that we could imagine from a volcanic, the kinds of pressures you get in a volcano. And he said that really the right hypothesis is that it is an impact crater, that's the only thing that could create the high pressures needed for it. And so the idea of impact craters got to be more widely accepted. You see, when we look at the moon, the idea of these craters on the moon, once Galileo had built his telescope and had turned it towards the moon, we had seen craters, but we had assumed that they were volcanic. Volcanic craters, again, widely known. Impact craters were unknown, or at least not understood. And so the idea that the craters on the moon were all volcanoes was the widely accepted idea right up until Eugene Shoemaker's discovery in the Behringer Crater in Arizona. This is maybe the best preserved, most spectacular crater of this sort because it's so young. It's only in the thousands of years old. I was going to say 10,000 years, but that may still be a little bit young. It may be a little bit older than that. We've got here a link to the Lunar crater lake in India there. I haven't seen that one. I'll have to take a look at that afterwards. There's also another one which has a nice ring lake, which is in Quebec, but it's very old. It's been scoured over by the ice caps during the last glacial period then. So it's much more worn down than this one in Arizona. Now, so the moon got to be understood to have impact craters, possibly also volcanic in some places, but also a good chance of being impact craters. Now, why don't we have many on the Earth then? Why aren't we not covered with impact craters all over the Earth? Because we got an atmosphere, for one thing. We have water, we have rain, we have weather, we have erosion. And so craters on the moon, if there's no air there and there's no active geology going on, they simply stay for a very, very long time. In fact, they would stay until they're covered up by another impact, making another crater on top of it. So craters on the Earth were not, the impact rate is so small. We had seen meteoroids fall to the ground then, but they generally didn't make big collisions. But again, in 1908, there was this unusual explosion in Tunguska in Siberia, in Russia. But nobody saw where the thing landed. There was the Great Fireball was seen then, and there was a glow for a long time from the dust scattered up into the atmosphere. For days in Europe, people could read newspapers after sunset from all of the glow of the dust in the air. But nobody was able to get to the location for years after the collision. And we still don't quite know what it was because there's no crater there. So these things have been very mysterious for a while. But the moon presents a much different kind of environment, an airless, waterless, erosionless environment, mostly erosionless. We can study these kinds of impact craters much more easily. Now let's take a look at the moon then. We get different kinds of craters depending on the size. Now, if you take the size of the object, I'll call it a meteor in general. The term is not really correct. A meteoroid is the thing that is left over after a collision. A meteor is the side of the fireball as it comes through the atmosphere, but the moon doesn't have an atmosphere. And a I've mixed up my terms. Meteorite is what's left over after an impact. Meteor is what's seen as a fireball through the atmosphere, and a meteoroid is what's floating around in space, which before any kind of collision. But I'm just going to say very loosely and incorrectly meteors. So the size of the meteor will give you the size of the crater. With a pretty rough scaling then, they come in at more or less the same kinds of impact speeds, which are determined by the typical speeds of objects orbiting around the sun at some numbers of kilometers per second then. And the bigger the impactor is, the bigger the crater will be. And there's a very convenient formula for this, which is in Mr. Hartman's book here. Now, if we've got a very small one, you just get a pit. I mean, this is just like sand grain sized particles that are hitting something. There was on one of the more recent space shuttle flights, of course, I guess that's been 10 years ago now, there was an impact with a little sand grain size or maybe a flake of paint that hit the windshield on the space shuttle, and it left a visible pit that the astronauts could see. Still small, but enough to the kind of thing that would cause some problems if you were out there on a spacewalk. But larger ones, let's say a kilometer across, are what we call simple craters. They have a rounded bottom to them and a raised rim, which you can see around here. All right, so that's a simple crater, what you generally think of as looking like a crater. But if you get larger, we get what's called a complex crater. In this case, a complex crater has a flat bottom and it has a raised peak in the middle of the crater. Still has the raised rim around the outer edge there. Now, why do we get a raised peak? The reason is that as it's on such a large scale, we have a larger region that's pushed down by the pressure of the collision. But as it's pushed down, even rock has a bit of elasticity to it. It's pushed down and it bounces back up. Imagine those slow motion videos that you may have seen when you have water dropping into a pool. The water drop goes down, and then you have a splash that comes back up with a raised drop in the middle, and then kind of a crown shape around the outer edges. This looks very much like the complex crater shape here. The reason we don't get that raised center part in the simple craters are because rock is not as fluid as water is. And so it's got a lot more rigidity than that. If you get an even larger one, here's the Schrodinger crater, which is 320 kilometers across. You don't get a central uplift, as they call it. You instead get a ring of peaks in the middle here. Now, if you get even larger still, 970 kilometers across, in this case, you get the Mare Orientalis. They call it here Orientale, I may be saying it wrong, which is in between being a crater and an impact basin like the Mare. And here you get multiple rings of uplifts. And in fact, they occur at a spacing of the square root of 2, which I find interesting. I think there's got to be a simple explanation for that, and the planetary scientists surely know what that explanation is, but I don't, because I haven't read yet. All right, so these are the kinds of shapes that you can expect to see. Now, take a look at what simple craters look like here. This is on the lower right is one that I showed you before. But these two in the upper and on the left are, again, quite simple. Notice again that they have rounded bottoms. The reason for this is that they have not excavated down into the deeper layers, which are more rigid. If we go up to a complex crater, well, we're not up to a complex crater yet. We make it a little bit bigger. We get a flat bottom. Okay, and here this one's a flat bottom on the bottom here. Notice that complex structures on the around this, those are not from the impact. These are actually landslides from the lunar regolith, which is the lunar soil, the gravel, which has slid down these steep slopes over time. Maybe from later impacts, maybe just from things eventually roll, and have formed dunes, basically, down in the bottom of the crater there. If we get larger still, we get a complex crater, properly called. This is the Copernicus crater, which is a very spectacular one with long rays stretching out from it across the, I always get Copernicus and Tycho mixed up on there. So I won't try to say exactly where this one is, but I think Copernicus is on the upper left as we view it from the Earth. But you can see that central uplift, a few peaks, but right there still clustered near the center. Okay, larger still, okay, no, still about the same size here. This is the Tycho or Tycho crater, which is down near the bottom of the moon, the southern edge. 45 degrees south there. And it has very bright rays that streak most of the way across the moon. Those rays are from material that was excavated and kicked up above the moon's surface and then came back down. As we get larger still, the Mare Orientalis, the Eastern Sea, which is on the eastern edge of the near side of the moon. And this is a small impact basin compared to the ones facing the Earth. But you can really see the smack shape that thing created. The big Maria are so big that you don't really see this kind of structure very easily. They've been filled in by those magma flows. Okay, so what about all these impacts then? Well, it turns out that as we understand it, we've been able to get a chronology. We've been able to put a time scale to it from the Apollo program. Now, there were two goals in Apollo. The first and really most important goal was to beat the Russians to putting a man on the moon. That was part of the big Cold War contest between us then. That was what had motivated everybody. But there was already the desire to go to the moon long before this had happened, and to get men on the moon and to understand what caused the moon. What's the origin of the moon? It's really the big scientific geological question. And to understand what's going on with how is the moon working today? Does it have moonquakes? What's the core of the moon like? Are there still impacts going on and such? And so these are the geological goals, the planetary science goals, which we carried out there. So from the material brought back from the moon to the Earth, we were able to get core samples, we were able to get rock samples and so on like this, and we were able to do radioactive age dating of them, and we could tell how old the surfaces were. From this, and from the material I'm going to show you shortly, scientists have been able to come up with a rate of impacts over time. And what they figured out then is, if you look at the bottom here, this is how many billions of years ago. Capital G lowercase yr is gigayears. You will also see capital G lowercase a, which is simply taking the Latin annus for year, so gigaon. And the geologists tend to use that for how many years ago, rather than just year of time, but it's how many years before the present. But you'll see those used almost interchangeably for looking backwards in time. So if you look here, the vertical axis is capital N, which is simply the number of impacts. And in parentheses 1 means the number of impacts that leave a crater bigger than 1 kilometer across. And they've got to scale it from some way. And this is the number of impacts of that size per square kilometer of area. So this is the density of cratering, of significant craters. And this is a logarithmic scale. So back 4.5 billion years ago, when the moon and the Earth were both new then, the impact rate was very high. And it declined. Here, we're looking at a log linear plot then, more or less like this. These time periods, the Noachian, Hesperian, and Amazonian, have been come up with, I think Tanaka, a Japanese astronomer, is the guy who came up with this terminology. Maybe in they cite a paper of his from 1986, and I think he was the guy who came up with these epochs then. All right, but we don't need to worry about those for this purpose. We care about the years, how many years ago. And so the rate decreased over time, and then it kind of settled out about 3.5 billion years ago. And it's been very slowly decreasing ever since then. The two lines you got here are from two different research teams, William K. Hartmann here, and Gerhard Neukum is a German name. I'm not sure entirely how to pronounce that. The two of them have worked separately and in this paper together, and they've got some different estimates there. So this gives you a range of the uncertainty, and then you see a steep drop off down to the present day, where we're still seeing impacts going on now. Now, this is one theory as to the rate at which the impacts have decreased. However, the Apollo astronauts brought back with them some interesting results that seem to indicate a region of heavy craters that was younger, in fact, 3.8 billion years old. When by that point, 3.8 billion years, you see where this vertical line is, the cratering rate should have decreased dramatically. This theory is called the late heavy bombardment from the Sea of Nectar, the Mare Imbrium, and the Mare Orientale. Although that apparently is less certain. We did not visit the Mare Orientale. So this is from maybe from some remote sensing that's been done by looking at the spectroscopy of the rocks there, so we can tell the geology of them. But anyway, there seems to have been evidence for a dramatic increase in the collisions about 3.8 billion years ago, and then it stopped again. And there is some evidence for this. It seems to be largely in the southern hemispheres of the moon and maybe of Mars and some of the other terrestrial planets. And the idea is that some motions of the gas giant, the Jovian planets, the motions of those as they were dragged inward by dynamical friction, they may have scattered some of these protoplanets and asteroid-sized impactors and other debris into the inner solar system, smacking into the Earth, the Moon, and the other inner planets for some periods of millions of years, called this late heavy bombardment. And then it drifted off again once that was done. The idea of the late heavy bombardment is not universally accepted. In fact, in this William K. Hartman book that I was relying on for my first idea for this project, he does not mention the phrase at all. And he's one of the pioneers of the field. So I've seen some other material lately that has questioned the existence of the late heavy bombardment. All right, but anyway, so what do we do with all of this then? If the rate of cratering is known, and whether we have a late heavy bombardment or not, let's say that we have a baseline measure of how many craters per year are produced. Well, if you look at a region of the moon and you count the number of craters per square kilometer in that, then you should be able to get the age of that surface. That is, what do I mean by the age? I mean, isn't the moon 4.5 billion years old or so? Well, yes, but by the age of the surface, I mean, since the last time it was paved over. Well, that could mean from magma flows, lava flows, or it can mean even from, if you're on Mars, for example, or the Earth, since the last time it was erased, like a flooding event that left a deposit of silt, okay, like a sedimentary rock. Or since on the Earth we have the tectonic plates and we have subduction underneath them, and things get brought back down into the mantle, right? And then we have the mid-Atlantic ridge where we have new crust that's produced all the time, all right? That's new surface there. So when was the last, how long has it been since that surface was created? All right, so if we understand the cratering rate at various times, we should be able to integrate that, but we've also got to know the distribution of the sizes of the impacts, because how many small ones versus how many big ones? Here's the thing. If you take a rock and you hit it with a sledgehammer, it's going to break into a small number of big pieces and a large number of small pieces. I mean, think it only makes sense, right? You can't break something into a large number of big pieces because you don't have enough material to go around. It's easy to make a whole lot of little pieces because that each one of them is only a very small amount of material. But in practice, we get both. We get both a small number of big pieces and a large number of small pieces. In fact, if you were to take this, one of my friends does an astronomy lab with exactly this, where they take a sledgehammer to a bunch of rocks, and then they put them through sieves that sift out the little pieces, the medium pieces, and the big pieces, and they count the number they get. And what you get is a power law distribution. So if you plot the number of pieces of a given size versus the size, you can fit a power law, a decreasing power law to that. So combine that with the cratering rate over time, and what you get is something like this. You can count the number of, let me explain the diagram first. This is a plot of the distribution of crater sizes in a region on Mars. This is again by William K. Hartman. So the vertical axis is the number of craters per square kilometer. But the horizontal axis is the size of the craters. What he's got here is, this is a histogram, and each of the bins is centered on, he's increasing it by the square root of 2, let's see, the square root of 2 times the diameter. I should say 2 times the diameter and take the square root. There we go. And so we're increasing by the square root of 2 each time, 16, 31, 63, so on like that there. Oh, wait, you know what? I'm wrong, sorry. Normally he does that with this one here, he's simply got it where it's increasing. It looks like he's doubling it with each tick mark, sorry. Most of his, he uses a square root of 2 distribution there, but that's not important to our needs right now. All right, so if you count the number of really big craters, which would be, this is how many kilometers across they are here for the big numbers, and you go down here, and for this point to the left, it's how many meters across they are. So watch your horizontal scale. And you count the number of big craters, and you count the number of small, medium-sized craters, and the number of small craters, and you see that you get on a log linear plot like this, or actually it's a log plot, you wind up getting a straight diagonal line, more or less. These are uncertainty levels here, okay, because you have statistical counts on these kinds of things. And so you have uncertainty, you have error bars. And but you can fit more or less a straight line to this. So what William Hartmann has done is he has done all the work with the integrals for you, and he has created a template of this graph where the dashed lines show if your count of craters lines up with one of these dashed lines, then that surface is that many years old. Here's 4 billion years, 3, 1 billion, 100 million years, 10 million years, and 100 million, 1 million year, and all the way down to 10,000 years. The template that I've got for you is his latest version, which goes even all the way down to 1 year. After all, Mars is geologically active. So what you need to do for this, you're going to count the number of craters in a region. You're going to measure the area of the region, and you're going to measure the diameter of the craters. So how do we do that? Can we just take any old map, any old photograph of Mars or the moon that we find and do it? No. Well, actually, you could, but you'd have to do a lot of corrections. Because if you get, say, a Mercator projection, you know that as you get closer to the poles, it enlarges the area. It does not preserve the true area. All these kinds of projections, map projections, distort things in one way or another. What we need is a map projection that does not distort the area, even if the shape is distorted. What we want is a projection which is called the orthographic projection. And I realize now that the black on medium gray was a poor choice of color for my label on the left. Should have used white. All right, so an orthographic projection is, you can think of it as the view you would have from an infinite distance with an appropriately large telescope. So all of your sight lines are parallel lines to the surface here. So we can make an orthographic projection of the Earth, for example, looking down onto the North Pole, or in B here, looking at the equator, or C, looking at any other position, any other latitude and longitude on the Earth. And that will be the center of the projection, and everything else will be distorted in shape, but the area will be preserved. Distances will be preserved. I should say, sorry, it's not, made a mistake. It's not the area that's preserved. There's a very specific property of a circle that I want to have preserved. Its diameter. You see, if you take a circle, let's say we had an impact crater on the North Pole here, and we're looking down, this is projection A, and we've got a circular crater. Let's say this ring right here is that giant crater. All right, well, that comes out as a nice circle, and we can measure its diameter very easily. But what if the impactor were down here at, let's say, 45 degrees north latitude, okay, right where my cursor is, if you can see that, across the middle of the United States or upper United States. In that case, we would see it look like an ellipse. It would be foreshortened. So how can we measure the diameter? There's something I picked up when I was a grad student at the Space Telescope Science Institute. There's a neat property of circles, and that is, if you take a circle, like I've drawn here at the top, if you were to draw that on a sheet of paper and then tilt the paper, it would become an ellipse. But the neat thing about the ellipse is that while it gets more and more elliptical as you tilt the paper, it does not change the length of the major axis. That is, the diameter of the circle can be measured even when you tilt it at an angle. All you need to do is to find the long dimension, which is the major axis, and measure that. That's the diameter of the circle as if you had viewed it from face on. Take a look here at a picture of the moon. This is from one of the mapping tools that I'm going to show you. And I have drawn in, well, not by hand, they have a template for it, the craters of certain sizes there in dark red. Unfortunately, the dark red doesn't show up really well, but you can see them. Now, if you look at these, which are, we're looking at the edge of the moon, the limb, L-I-M-B, of the moon, over here on the lower left. But closer in the upper right, we're looking almost face on, and you see that these are truly looking like circles. And over a wide area, the circles still look like circles. There's a minimum amount of distortion. But as we get over to here, this is the Tycho crater, I believe, right here. You see the rays, the streaks coming out from it, way across the moon there. It's noticeably foreshortened. It is an ellipse then. As we get closer and closer and closer to the limb, they become much more elliptical ellipses. But in every case, we can measure the diameter by measuring the major axis there. That is possible with an orthographic projection. There are some other projections that would also do the same. As long as we get an ellipse, we would have that the case. Let's see, stereoscopic. I don't want to name the others because I haven't checked on those. But an orthographic one will do it. Now, the great thing is that the tools I'm going to show you will give you an orthographic projection. So I'm going to leave the slideshow now. Let's see there. All right, leave the slideshow. And I'm going to pull up my web browser. Let me get it to the right page first. Okay, I'm going to share correct one. Actually, I'll put it on desktop too, so I get the whole thing. And you'll be able to see my cursor, I hope. Okay, let's make this larger. Okay, so what we need is a tool that we can use that has a map of the moon and it has a scale so we can get the size of things. Now, you could do it with anything. I've got, let's see where. I have here, making a dramatic pause right now. I've got some printed maps of the moon, and you could do it with those. This is a US Geological Survey. I'm sure other countries do the same. And here is a map of the moon, as you can see mine here. And it has a scale on it. But the thing is, it is a, what's the projection used here? This is this is a NASA. US Geological Survey prepared for NASA. It's a Mercator projection. So it's very distorted as you get away from the equator. But you can see barely down here, it has the scale for different latitudes. So you would be able to do it if you got a ruler and you were very, very careful about how you measure it. And so that's actually a nice low-tech method if you go on and get these maps. Now I'm going to type this into the chat window here because you can order these yourself. Then I imagine they ship anywhere in the world. US Geological Survey maps of the moon, and you just pick the which region you want and so on like that. And they've got a website, usgs.gov, I believe. But you might have to check that. So, so you can get that. That's one option there. But it's that there's a convenient option several convenient options to do it in the computer, which will allow you to get the orthographic projection and the measurement tools themselves. So here's one of them here. If we go to the LROC, the Lunar Reconnaissance Orbiter, they have their Quickmap. So this is one that's pretty useful. And what you can do, let's see, I'm going to close this out. Come on. Edit, click again on feature. Now, how do I delete? Well, okay, I'll have to. All right. So if you go to the Lunar Reconnaissance Orbiter's Quickmap, you can zoom in and out. In fact, you can get down to very, very fine features here. I'm going to zoom out so you see where we're starting from.
Tim, could you please cut paste the URL in the chat?
Yes, I've got that on there.
Okay.
Quickmap.lroc.asu.edu. Let me put it with the HTTPS first, and people can click on it then. There we go. That should work as a clickable link now.
Thanks.
Okay, so here we have a region of the moon. Now, if you click and you drag, you simply shift the view around. All right, we're looking at the lunar near side. We can zoom down onto, let's go to a region, something interesting. Let's go right up here. This is I forget which mountains these are, the Apennines maybe. And it's just two fingers scrolling up and down like that on my laptop, on the trackpad. And if you're using other tools, then I guess you can do it with the mouse with a little scroll on that. And they do have plus and minus to zoom in and out. Okay. So I'm scrolling around like that. Let's get down into this region here. All right. Now you see down at the bottom, you've got you have a reference scale here. 5 kilometers is that size there. And if you wait for a moment after you zoomed in, it will load up the higher resolution data. Notice that sometimes it comes from multiple photographs, making a mosaic. LRO was taking pictures for years and years, and so they have it. They may be at different angles of the sun and things like this, but you'll be able to get the higher resolution. Okay, I'm going to go down to one of these tiny craters here. Notice how you get almost a fractal kind of a feel to this, because you're looking at the same kinds of distributions of crater sizes, relative distributions, no matter what scale you look at there. Again, because it is a power law of sizes. All right, now what you can do here is, you see on the left, we've got overlays. What we can put on it, LRO satellite, we don't need that here. I don't need to put the overlays on that. You just click on one of these tabs to get the menu on it. Geologic features and maps. You can have it outline craters of various sizes, which is what I've done on that illustrations. Wrinkle, all kinds of interesting stuff if you want to get into lunar geology, which I think is a really fascinating topic. Okay, and these are from LRO's Lunar Reconnaissance Orbiter. Lunar Prospector was a different satellite. Grail is a gravity measuring satellite. Chandrayaan-1, is that an Indian satellite? Is that the new one?
Yes, yes. No, that was the first one. The first. That's
Okay,
one.
all right.
There's two also.
Okay. Clementine was a one back in the 1990s. That, by the way, there's an American folk song called "My Darling Clementine," and they named it Clementine because the chorus of the song goes, "She was lost and gone forever, lost and gone forever, oh my darling Clementine," and because at the end of the mission it was flung off into space, then lost and gone forever, and so on like that there. But we don't need those there, so I'm going to go from that. All right, what we want instead, I had it up. Draw and search tool, here we are. Okay, so the second one down, draw search tool. You have a point, an arc, or a polygon. Let's go with the arc first, which is just going to, it will, among other things, let you do a straight line or a curved line. I'm going to select it. Now, notice it gives you the instructions. Click to add vertices, double click when you're finished. So I click on one side of the crater. If it's foreshortened, because it's up near a pole or the limb, you simply look for the long dimension. So it looks to me like from here to here is the long dimension. Try to get it at the top edge of the crater rim. It can be hard to judge on some of these small ones if you're zooming in a whole lot, but maybe not, all right? So right about here, notice that again, it's going to slope down on the outside. So I'm going to get right about there. I click once here, and I'm not clicking and dragging. I'm simply clicking once, and then wherever I move my cursor, it goes with me. Now, when I'm done, I double click. Okay. Now I put on there, let's see, it saves the old one. Oh, that's how I erase the old one. Delete. All right. Now I've got path number 1. I select it, and it gives me geometry. And look here, distance 0.167 kilometers. So what you're going to do is you're going to keep a table, and you're going to draw those lines across the craters, and you're going to write down the distance. Just copy and paste the distance across the diameter, and you just keep going. Now, to know which ones you've already looked at, well, leave the drawing on there. You can do another one while you're at it. So I go here. Oh, I've got to go to draw tool again. There we go. Now, wait, why is it not going? I'm going to select arc again. Sorry, I've done it a little bit, but not a lot. I go there, I double click, 0.048 kilometers, and so on like that. So what you might want to do is to start off with the largest ones, because there are fewer of them, and work your way down to smaller ones until you reach a point where you think, I've had it. There are too many to start counting all of them here. So, but you need to know what the minimum size you're measuring is, because if you measure, you know, a few of them of a given size, but you decide the others, it's not really worth my time there, and they're the same size, you're going to get a biased result. Okay, and you leave them in place so that when you zoom back out, you know the ones you've already gotten. Now, take a look here. You can see older craters and newer craters. The newer craters have sharp rims, very clear edges to them, like this one here. So I'm going to go to, let's see. Oh, there we go. Close it, draw. All right. This is a new crater here. There to there, double click. All right. But this one here is a very old one. The reason I know it's old is for two reasons. One is it has a very indistinct rim. It's very smooth. It just kind of gradually tips in there. The second reason is you see that there are other craters on top of it. So here is a basic working theory that you do in geology is that craters go on the top of existing craters. So if you see whichever is youngest is the one that's on top. So if you see little craters on top of a big one, the little ones are younger than the big one. If the big one came later, it would have obliterated the little ones there. So that kind of goes along with what we expect, yes. And you can see a few others, these very smooth ones here that are old. All right. Now, if I zoom back out, we can see much larger craters. Okay, so here's a big one. This one is in between simple and complex. I close feature info and go to arc, and let's find the longest distance across there. Double click. At 16.5 kilometers. That's a decent sized one there. And we just go on like that. So this can be tedious, but again, if you start, it's better if you start off with the biggest ones in the region you've chosen, and then you gradually work your way to the smaller ones, and you can get to a point where you say, this is small enough because at this point, if I go any smaller, there's simply too many for me to bother with. Now, Ankur asks, is every depression on the surface a crater? No. Every circular or elliptical depression is likely to be a crater. If you take a look, in fact, right where we are here, drag around, there is another feature which is not a crater here. Okay, you see this canyon coming out like this. There are two of them side by side. These are called rills, R-I-L-L-E, which is meaning a canyon, basically. And these rills, this one, very often, these are from lava flows. They could be channels cut by flowing lava, or they could be collapsed lava tubes, lava caves that have gone on. And, but this is in between where maybe there's been some slumping of the crater rims of these here, so I can't guarantee what caused it. But Apollo 15, for example, had explored at Hadley Rill, which is a very large one, and that one is probably from flowing lava. Here's another rill, so you can see that long line here. Okay, so but if it's round, it's almost certainly a crater. There are a few other things that are round. Very rarely there are caves that have caved in, sinkhole basically, and those look a little bit different, but you're unlikely to find one of those. I don't know how many there are. Oh, by the way, here's a very young crater you see with the white spot there. It seems that the lunar soil darkens with time, with exposure to cosmic rays. And
what is the explanation for rills? How are they formed? These long.
Say that again.
I said, what is the explanation for these rills? How are they formed, these long structures?
I believe that most of them are thought to be lava flows, but they would be channels cut by flowing lava.
Okay.
On Mars, there are other kinds of canyons and valleys which are indeed water riverbeds. But on the moon, we don't think that there has ever been any flowing water. There is, however, frozen water, ice, that's mixed in with the soil down in the permanently shadowed regions at the South Pole. In fact, there appears to be a large amount of water ice. But because there was no liquid water, then this is surprising to me. I just found out this past weekend, earlier this week, that there was a Lunar Surface Science conference that I attended. And we had a talk by Jack Schmitt, Harrison Schmitt, Apollo 17 astronaut, and the only scientist to have walked on the moon. And his talk was showing about the lunar geology, and the guy who came after him was the guy who had trained them for the geology on the moon. And he said that there are 4,000 types of minerals known on the Earth, and there are only 100 types of minerals known on the moon. And a big reason is that there's no air, so no oxygen to mix with the rock, and there's no water, there's no standing water. And so you just don't get the kinds of minerals that takes. Now, I'm already running up on 2 a.m. and I think I don't know if you had me scheduled for just 1 hour here. So
That's okay. There's nobody after you.
okay, right. I won't keep you all too much longer then. So the technique is the same. Again, start big, work your way smaller until you hit your exhaustion limit, but make sure that you have a well-defined minimum size that you're going to measure. And you're doing these in bins, so there's going to be a range of sizes in each bin, but you've got to know the minimum one that you're going to be able to measure. Now, the scale that you can measure on this in a given single picture is going to be pretty constant. But if you're looking at something where you have a blurry picture and then a sharp picture next to it, you've got to make sure that you don't measure really tiny features on the sharp picture, and then, well, you can't see them on the blurry one, and so you only count bigger features, because again, you're going to get a biased result. So let's see how this works then. Actually, I'll show you how it works. Let me show you other sources. So the Quickmap on the Lunar Reconnaissance Orbiter page at Arizona State University here is a very good one to use. I'll show you some other simple ones, and then I'm going to show you a spectacular one, but it does involve doing an installation on your own computer. All right, let's see here. There is the Trek website at NASA. Now I'm going to put this on here on a clickable link again. Okay, the Trek website has the Moon, Mars, and several other terrestrial planets, as well as rocky moons. And I'm looking at Mercury right here. Now, it has a much simpler interface, but not in a good way necessarily. It has a lot more stuff you can see here. So I'm looking at Mercury. I can zoom in and out the same way I did with the Moon, a little bit too quickly perhaps. And it looked like I tested that out with measuring there. So I'm going to hit the layers there. Downloads. Okay, not that. I hit instead base maps. Menu. Here we go. Calculate distance. They really hide this. Calculate distance. We hit line. And we press down to start and let go to finish. So you click and drag in this case. Let go. And you have to wait for a moment. It's a little bit slow. And then it comes up with the size. All right. So you can do that. Now, here's the thing that I forgot to mention. Take a look back at the Quickmap here. You need to calculate the number of let's see, I'm thinking of my normal research. You need to calculate the density of these per square kilometer. So over a region that you measure, you've got to define what the region is, and you need to know its area. So on the Lunar Reconnaissance Orbiter map, close out feature info, we go to polygon. Let's say I'm going to measure this region of one of the mare. You can simply create a polygon of the shape you want, and then I double click when I'm finished, and what you see is it calculates the area for you. So you've got to define the region you're going to use then, calculate, measure the craters within that then, calculate the area of the region and the number of each size of crater, and bin them up like that and go from there. Okay, now, so you can't do the area with the Trek website at NASA. However, you've got Mercury, Venus, and I think Venus and some interesting moons. Not all of them had the distance measured though. All right, but I thought Europa would be interesting because Europa, which you're seeing here, Jupiter's moon Europa, is covered with ice. And we believe it might have a global ocean underneath it there. And so it presents a very young surface. There is very little cratering. Actually, that might be a crater right here. Ooh, too close. That might be a small crater. But this is ice, and so it is a young surface. These cracks are where it is broken out, water has come up through, and it's refrozen. So it's constantly repaving. So you see very few like that. That'd be interesting, except they don't have the distance measure on Europa, which is a real shame. Okay. I had one other here, which is the Lunar Global Explorer. But really, this is, again, the moon, and the Quickmap is better for that. But let's go to the spectacular one here. All right, JMARS, which is, you might think it stands for Mars. It stands for Java Mission Planning and Analysis for Remote Sensing. Yeah, it actually stands for Mars, but they figured out what it was going to stand for. They came up with the acronym first and then came up with a cutesy thing it would stand for. All right, so this is... if any of you are familiar with what's called GIS, that's Geospatial Information Systems, it's a new-ish topic in mapping and geography. I guess it's been around for a while, but it's much easier to do these days. And this gives you a nice GIS thing where you can map over several different kinds of layers, different kinds of maps on it. But you've got the distance measurement and the polygon tools to calculate distances, diameters, and areas as well. But it has more than just the moon. It's got Mars, and it has other planetary surfaces. I would demonstrate it for you, except my office computer here, my laptop, I take it home, is 5-6 years old, and I have been afraid to update the operating system on it for a while. Because some of my research software can't use the new operating systems. But unfortunately, the JMARS doesn't use my old operating system. So I might upgrade it just a little, like one step in the OS to the new-ish Mac OS. But anyway, so I can't demonstrate it for you, but they have tutorials here. You look on Getting Started. Oh, let me give you the website. And I'll send to Priya a list of these websites so that everybody's got access after the chat window is closed up. But you might want to copy that down for right now. So you go there, and they've got, if you go under Getting Started, on that, they have training videos, a slightly older version of it, but the same tools are still available. Oh, that's where I am here. Let's go to documentation, tour of the interface, introduction tutorial video, so on like that there. So, I'd let you explore that at your leisure. So anyway, the materials, let's see here. I didn't get out the templates. Let me get those for you. And I will post those in the files, and then I'll send copies to Priya as well for safekeeping. I've copied templates for these. Let's see here. What these are called are isochrons. Now, if you're doing any like stellar evolution or galaxy evolution, you might know the word isochrone. And this is basically the same word, spelled a little differently and pronounced a little differently. But it means basically the same thing. So here's the template, and these dashed lines tell you that if your plot, your histogram, lines up along that line, that's the age of that surface. There are a few features that we need to pay attention to, though. For one thing, you notice that these things curve in weird ways. There are some reasons for it. This you can only use as a template for a given moon or planet. It won't work for the others exactly. Mars and the moon are noticeably different, not dramatically so, but enough that you could get wrong. So notice here that there is a tip over at the top end. The number of craters per square kilometer, like that, it tips over and levels off at the top end. The reason is, a couple of reasons. These are very small craters on the left side. you would expect there to be more and more and more going as just a straight line on a logarithmic versus logarithmic plot, but you get a little bit fewer at the top end because Mars has an atmosphere. So the smallest particles that would create the tiniest craters burn up in the atmosphere and are gone. So you don't get them, but not all of them, because it depends on the material. The iron meteorites don't burn up as much, but the stony meteorites do burn up more. So you get some stony, some iron like that. And it doesn't mean that all of them are gone. Furthermore, Mars has a bit of active geology. It's got the atmosphere, it has a bit of erosion, and so that erodes the smallest ones fairly quickly. On the Earth, of course, we get impacts all the time then, but you rarely see a crater, a very new crater, because it's dirt and water floods into it and it erodes it within a few years. So the same thing is going on the Earth here, but you've got a tipping over of that. Let me show you. I've got, as an example, I scanned in the isochrons templates and the data for everything in Hartmann's book. Let's see here. Mars, meteors, here we go, scans page 1. Let's take a look at that. Okay, and he puts it black on gray, which I admit is a little hard to read. So he's got here in his book, he's got the dotted, the dots there. This gives you a sense of the uncertainty in each one. Each one is labeled with the age of the surface, if it lines up with that. And you just plot your dots along here, and you see if it lines up with one of those or another. He's got lines for various regions on Mercury, Mare and the Caloris Basin, the uplands, and so on. The moon here, you see Tycho crater, Mare Imbrium, different ages. Tycho is younger. The seas are older like that. Some of the seas are even older still. But notice that in all of these, you get this heavy black line called the saturation equilibrium. This is really neat. If you get, over time, if you keep cratering, eventually there's no room left, there's no uncratered surface left, and any newer crater simply obliterates some of the older craters because it's got to hit one. So that means that there is a maximum number of craters per square kilometer that you can have. And that's that saturation there. When everything's been cratered, so when you put in a new one, you remove some old ones and you can't make any more. And so that is a constant line for every planet or moon. It'll be in the same place. Let me bring up one more of these before I show you the templates that I made. Okay. These are little notes to myself here. Look, here it is from Mars, and notice how on some of the surfaces on Mars, the south polar sediments, see how it tips over at the smaller ones like that? That's because there is enough active geology that's erasing the smaller ones. But you see on the larger ones, it starts to go parallel, and it starts to become fit the parallel to these isochrons. Okay, so you can determine the ages of these here. Galilean satellites, these are moons of Jupiter. Ganymede, let's see if they've got Europa. Here we go, Europa, like that. Definitely a younger surface like that, but still tens of millions of years old. Phobos and Deimos.
Sorry,
Like
Tim, but there's a related question. Does
Yeah.
the surface gravity and the surface density of the surface layers play any role to the diameter of the crater?
Yes, yes. The density of the materials at the surface play a small role. I have seen some of the more recent papers where they work up whether you're dealing with bedrock or sand, for example. But with these big impacts, I think that it doesn't make a big effect, but a relatively small effect. However, the surface gravity does play a role. That is one of the reasons for the difference between the location of the isochrons for the moon and Mars. Let's see here. Okay, if you can put the moon and Mars side by side. Okay, there we go, moon and Mars. And you can see, here we go. You can see a very subtle difference on where those isochrons are. See where they come down and where they intersect the diameters on the bottom edge. One of the reasons for the difference is that the moon has it's a smaller gravitational pull. And so it is less likely to pull in one of the impactors to hit the surface at all. Mars is more massive, and so it's more likely to pull in something that would have missed it if the gravity were weaker, but instead comes in and hits it. So that surface gravity plays a role in attracting the objects, and it might also it'll certainly accelerate them more, and so they'll hit at a higher speed, but I don't know how much difference that is because they're already moving at some number of kilometers per second. So I'm not sure if that plays a role in speeding them up enough to make a difference. But anyway, that's a big deal. And again, if the Mars's atmosphere plays a role in burning up the smallest ones there. So I have made templates, isochron templates. Let's see here if I got them. Yes. I have traced over the ones for Mars and the moon. So here in gray are the isochrons with the typical uncertainties that Hartmann puts for them. Saturation equilibrium there. I've written the ages on the side here. And so you can just plot it on paper that way. Here it is for Mars. So you've got those, and I've also got the more detailed one, which has them all the way down to like 1 year if you chose a very young surface. So the idea is choose a region. In fact, you might choose 2 regions, that would be best. One that is very uncratered and one that is heavily cratered, and then compare the 2 to see how old each one is. All right, I think I've run my mouth long enough on the presentation. Happy to take other questions that you have.
Yeah. So you can unmute yourself and ask, or you can use the chat window. Actually, some of the questions I asked you while it was on itself. And, now what is the, if you could just list out, what is the project? What do students have to do? Can they choose the surface they want, and what do they do?
Yes, so choose, probably I would recommend if your computer is able to use it, use that JMars tool so that you have access to more than just Mars or the moon. You've got other things as well. Although I have the templates only for Mars and the moon. Although I will also post these for other bodies, and you could try making your own template from it. Choose a body, a heavenly body, and then choose on that 2 surfaces. One that is heavily cratered, one that is not cratered very much, and but it has enough craters for you to count. And then create the histograms, do your crater counts, make sure you measure the area around it, which you can use with the JMars, and you can use with the quick look one for the Lunar Reconnaissance Orbiter. Make sure you get that. Do your calculations. You can use a spreadsheet for it very easily for that to get the density, number of craters per square kilometer. And you're going to calculate it. You're going to bin them up. And so you look, and on the bins we have here, these bins are centered on this. So you're going to have, this bin here is going to be the one that has a diameter of 2 kilometers in the middle, and it goes down to, let's see, actually, you know what? Probably it's best to put, these should be the bin edges, 1 kilometer, 2 kilometers, 4, 8, and so on like that. Or here you've got, we got the same numbers there. And so this way, you're going to be plotting the dot in halfway between these 2 limits then. So anything from 1 to 2 kilometers goes in this bin. And then you can calculate the per square kilometer that way because you've got the total area.
And what is the minimum area they should consider? I mean, what are the typical numbers?
I've actually looked, I thought you would probably need to get a very large area, like an entire mare on the moon, but that's actually not the case because you have, depending on the area you choose, you'll still have a lot of craters. This should be it. You should choose one that has enough craters so that your statistical error, this is a Poisson distribution because you're doing counting statistics. So the uncertainty in the number of craters for a given bin is the square root of the number you counted. So it's going to be however you counted in, and it's going to be plus or minus the square root of n. So when you plot that on your template there, you see for ones which have very few counts, your error bars on the lower edge, because it's logarithmic, are going to be very, very low. So what you want to do is to choose a region where your error bars aren't all going all the way down to the bottom. I should note that you see that all of these templates here go no lower than about 10 to the minus 8th craters per square kilometer. On Mars, a little below 10 to the minus 8th would be one crater for the entire planet. So that 10 to the 8th or so is the surface area of Mars. And so that's why he doesn't bother going below that. So choose one where you've got enough statistics to make dots that go up here without the error bars all going to the bottom. For the really big ones, you probably will have like, one or two, something like that, and your error bars will go all the way to the bottom, but that's fine as long as you've got some smaller ones as well. And then measure the ages. I don't have answers for the correct ages on these, although if you look here, he does have for a few of them. But and actually, that would be a really good project for looking up in the NASA's ADS, the Astrophysics Abstract Database Service. Find a research paper that talks about that particular region on the moon or Mars and see what the latest results are on measuring the age. You should be able to do this. This was all done manually decades ago, going back to the 1960s. And so I think it should be doable to, reasonable precision by students today even.
Mm-hmm. Yeah, very interesting project. I never ever paid so much attention to craters.
I'll tell you, I had a student who was starting to do it for Pluto because the new results from the New Horizons mission had come in back, 10 years ago. But here's an interesting thing. And in fact, I would encourage people who want to go to Pluto, to try doing it with Pluto to do that. I believe that the JMARS system does have access to the Pluto data. And I've got a friend, I'm going to give you her contact information because she said the students can contact her. She's a planetary astronomer at NASA's Goddard Space Flight Center. And if y'all have questions on it that I can't answer, you can ask her. And she volunteered this. I'm not putting her up to it. But anyway, she was the one telling me about the JMARS interface. And so I think she mentioned Pluto. Now, here's the thing about Pluto. It has a lot of ice. It has glaciers on it, and they're flowing. So you have we expect there to be very young surfaces, as well as heavily cratered regions, which are older surfaces. But Pluto is in the outer solar system. Was the cratering rate the same way out there at Pluto as it was here next to the moon? Remember, the moon is the only place where we have had a sample return mission, the Apollo missions. So we don't have any rock samples from any of the other planets out there to do the exact dating. The estimates for Mars have been done based on analogies to the moon. And the assumption, this is assumption number one that they put in the papers, is we assume that the cratering rate on Mars is dynamically related to that on the moon, and with some corrections they can make for gravity and so on like that. But Pluto, who knows? These kinds of things that hit there may not have gotten scattered out to Pluto. Mm-hmm. So we can't get an absolute age range on that, but you can still make the plot, and you can see where it would be if it were the inner solar system. It could tell us something about that. Mm-hmm. I see there's been a couple of questions here. So I've already answered Mrinalini.
Yeah. There's only the last one, which I had saved it for the end. It's just a curious question. Do we have the technology to deflect life-threatening asteroids? So I left that with you.
No, but we're working on it. So I should say that...
The movies we do.
Yeah,
America can save the world.
Right. I'll put myself back on now here. So we don't have a system to deflect them yet. But this has been a big concern of people. I would say ever since 1994, 1995, with comet Shoemaker-Levy 9, that Eugene Shoemaker, the geologist who had figured out that these were impact craters on the moon, he and his wife, she also helped him in these searches, comet searches, and David, I believe it's David Levy, who is their partner in this, they were running these searches for them, and they found this comet. And then they worked out the orbit, and they figured out it was going to impact Jupiter. Well, it made a pass around Jupiter, and the tidal forces on Jupiter broke the comet into, I think, 26 different pieces. And back in 1995, I think it was about a year later, it smacked into Jupiter, one piece after another, hitting that there. And we could watch it hit right on the limb of Jupiter. And the Hubble Space Telescope was able to watch it piece after piece and keep taking photos, almost like a video, which showed us the destructive power of these. Go back and look in the Hubble Space Telescope photos of Comet Shoemaker-Levy 9. It's fantastic what it did. It left Earth-sized gaps in the clouds. Well, this was the first time we had ever seen this happen. Gene Shoemaker and David Levy had been claiming for years that the solar system is still has active impact events going on, large-scale impacts. But people had thought, no, what, these things have mostly gotten swept up and there's no more major collisions, just little, meteorites, and that's all. And now we saw it actually happen right before our eyes. At that point, we started to wake up and realize we could be in real trouble. If one of those things were coming to Earth, it would destroy the Earth. So, the Earth's gravitational pull is weaker, so it would actually be a little bit less destructive than it was on Jupiter, but still very, very bad. Now, the last major impact we had was 100 years ago in Siberia. We haven't had one of that size since, but those things of that size happen roughly once every 100 years. Now, that doesn't mean it's overdue. It just means, statistically, we should expect one anytime. We did have another one that hit Russia. Why do these things keep hitting Russia? Well, it's a large country, for one thing. That hit Russia, or maybe it was the Ukraine, about 5 or 10 years ago. Maybe 2012, if I remember right, something like that.
I think it was Ukraine. It was Ukraine?
Okay. And it was smaller, but it still created a shock wave equivalent to that of a small nuclear bomb, and it injured a number of people from flying glass. The thing was, they were standing at the window watching as this bright flash went off, and then the shock wave comes in. They don't hear anything. Shock waves are not like you see in the movies. You don't hear a low rumble as it approaches you. You hear nothing. And then smack like that, it hits you all at once, like a shotgun going off next to you. So they didn't know the shock wave was coming because they can't see it. And they got hit by the glass of the windows there. So we've woken up to the problem. NASA is looking at surveys to look for these things. There are Priya, you can remember the name. What is the new big observatory coming on in Hawaii that is going to do the all sky survey every 3 days?
No, that's LSST, right? LSST?
Yeah, LSST.
I mean, Vera Rubin. Now it's Vera Rubin.
Vera Rubin, okay. They still kept LSST for like the survey itself and Vera Rubin for the telescope, I think. So the Vera Rubin telescope is going to cover the night sky every 3 days, a third of the sky every day. And they'll be able to find a lot of these. Before now, most of these comets and asteroids have been found by amateur astronomers, not by professionals. And the reason is there are a whole lot more amateur astronomers out there. And you need a wide field of view because you don't know where you're going to be looking for. And you just need to keep looking and looking and looking. We professionals take a small field of view with a high magnification, and we're looking at something specific. Rarely does an asteroid just happen to cross through that path. But the amateurs are looking for this stuff, and that's why they saw it. But now I think it's going to become more professionals and automated surveys that find these things. But we'll find a lot more of them, and that's a good thing there. So as far as deflecting it, sorry, it's taken me around to come around to your question. We don't have the technology now. I should say we have the technology in principle, but it's a matter of how do we implement it? There are 2 or 3 basic ideas. One is send a nuclear bomb up there on a missile and blow the thing up. That could be good or it could be bad. And the reason is, thank you, Priya. She's put the link there for the Chelyabinsk meteor. That's it. That could be good or it could be bad. It makes it into a much smaller pieces, but it makes a lot more of them. That means that it spreads the destruction over a wider path. On the other hand, if it makes the pieces small enough then they burn up, a larger fraction of them burn up in the atmosphere and are less dangerous. So, you know, there are kind of debates on the safety on that. It actually, I think it's not as bad as some of the people think. It could be an improvement. The second thing is you explode a bomb near it and you use the shock wave to push it away. All right, now that would be a sudden impulsive kind of force given to it. The thing is, you've got to do that early, because if you try to do it right before it's hitting the Earth, then you can't move it enough. Even a nuclear bomb can't push it enough to move it away. You'd have to have a greater force to do it if you do it very, very close to the impact time. The third option is you use a small force over a long time period. Solar sails or even high-powered lasers that give a small, just the force of the light itself would deflect it enough if you catch it early in order to move it to where it won't actually hit the Earth. So those are the three options there. We've got the nuclear missiles today. So options 1 and 2 are feasible in some way, but you still need a large rocket. You can't just put them on a typical intercontinental ballistic missile, which is meant to go up and to come back down. You want to put it on something that has escape velocity. And for that, you're going to need something like the NASA's SLS, the Space Launch System, which is supposed to fly maybe next year, but as NASA, it keeps having delays and such. That's one that you could put something like that on. In principle, we could do that today or as soon as SLS is flown. The others take a bit of work.
Yeah. So any more questions? Yeah, thanks. So they could even, yeah, so one would be a comparison of the bright side, the dark side of the moon, or moon Mars, or moon Mars Pluto.
Or even two regions on the near side of the moon there. Moon and Mars could be a great one. You could take a look and see, I mean, you're comparing different surfaces on them, of course, but just, you know, find a heavily cratered region on the moon and a heavily cratered region on Mars and see. But I think Mars would be really interesting because we're still learning about it it's much more recent that we're learning about Mars, because Moon is right up close to us, but Mars, I mean, it looks like that through a telescope, right? And so it's the spacecraft that have given us that close-up view of Mars, and we've got very high resolution maps now. And Mars has active geology. We have seen flash floods, liquid water that gushes out and erases sand dunes and things. We've watched this active, we've seen landslides on Mars. We've watched them happen while the cloud of dust goes up from it. We've seen tornadoes and things on Mars. Mars has active geology. That might be the most fascinating one there, to see something that is a really young surface.
Mm-hmm. Yeah, I think it's a very interesting, very different thing. I'd never thought about it. But yeah, on the one hand, it seems so obvious, right? That this can be done. But right. I think it's a laborious task. This would actually work out for a citizen science kind of project, right?
Yes, because it is one of those things that you can farm out the search, the measurements to a lot of different people. In fact, one of the Zooniverse projects a few years ago was measuring the craters by using a little ellipse drawing tool to look at craters on the moon. And Arizona State has had projects doing citizen science for looking at features on Mars. And so some of the stuff has been done that way. But to my knowledge, it hasn't yet been done with the crater diameter measurements of exactly this. And that could be a great thing where, you know, several get together and they kind of each one divides up with a little bit of a region there.
That's right. Because actually it's a very wide amount of work that can be done, right?
Yeah. Oh, by the way, you were asking about how small a region can you go to. I was seeing some of the papers where they were looking at the regions immediately surrounding a large impact crater, or even a medium-sized impact crater, so that, you know, the crater excavates and then it puts dirt down on and covers up the surface. So now let's see how young that surface is surrounding it, and we could be able to tell how long ago the crater was formed.
And probably a relation could even be done in, you know, those second generation craters, in the sense you have an old crater and then you check on the number of second generation, third generation craters.
Oh, that would be a good one there too. Right.
And, you know, that would also be an interesting thing, right? Because
you could tell the age of one of the craters on there, or several of the craters on there, by looking at, how many are on top of it there. Yeah, that's a good idea.
Specifically for craters which have a multiple generation, further ones over them.
Yeah.
Because I think we should let you go now.
I will say, even though this is coffee, it's decaf, so I should be able to get on the seat.
Okay. So thanks a lot, and we meet next Sunday again. I don't see any more questions.
Okay.
But I would really request, participants, since this was a more open projecty thing, if one can, actually list out what are the things that one can do. I'll try doing it myself, but the others can also list out. They can plan their project with all the stuff you've told them.
Yeah. And so let's see.
Thanks a lot.
To active galaxies and spectroscopy.
Yep. Yeah. And just for information for people who are newcomers, there has been a part 1 of AGN spectroscopy, which is available on YouTube. So I would request you all to see that one. I think that would be required before doing this. Right? There will be some amount of overlap, but it would definitely be good if you watch that. So please do watch that. Right? Yeah. So see you then. Thanks a lot, Tim.
All right, you're welcome.
And see you next Sunday. Yeah. Oh, Saturday night for you. Yeah.
Yeah, right.